6.4 is on the Central Limit Theorem and its wide application and use in statistics, especially with these normal distributions. Or I should probably say approximately normal distributions. The Central Limit Theorem is for all samples of the same size n, with n being greater than 30. The sampling distribution x bar can be approximated by a normal distribution with a mean, mu, and standard deviation sigma divided by the square root of n, where mu is the population mean and sigma is the population standard deviation. So given a population with any distribution has mean, mu, and standard deviation sigma. Simple random samples of all of the same size n are selected from the populations. It should be noted that this does not matter what type of distribution. Doesn't matter the underlying distribution itself. It's that for any distribution, as long as the sample size is at least 30, if the sample size is greater than 30, then the distribution will be approximately normal. Now, with that being said, if it's highly skewed, you might need a bigger sample size, but that's outside the confines of this video. The requirements, though: population has a normal distribution, or the sample size is greater than 30. The mean of all values of x bar is that the mean of the sampling distribution of x bar is equal to the population mean. The standard deviation of all values of x bar, the standard deviation of the sampling distribution of x bar is equal to the population standard deviation divided by the square root of the sample size. This is also referred to the standard error of the mean, right? Or just standard error. Standard error. And we could convert the z-score if we wanted to, for x bar being, we take x bar minus the mean, population mean I should say, divided by the population standard deviation divided by the square root of the sample size. And if the population is not normally distributed and the sample size is less than or equal to 30, the normal distribution may not approximate the distribution well, and we would need non-parametric tests of bootstrapping to accomplish this, which we will see later in the course. A couple of considerations. We first need to check the requirement of the population is normal or the sample size is greater than 30. We need to determine if you are using an individual value or the mean x bar from a sample of n values. If it's the individual value, we just plug the mean and the population mean and the population standard deviation in for the calculations with the normal distribution, just as we have been doing. But if it's a mean from sample values, we need to use the population standard deviation divided by the square root of the sample size for the standard deviation. And of course, in order to get this to be a perfect result, would be to either not round this value at all or carry out to as many decimal places as is humanly possible. So for example, women have normally distributed pulse rates with a mean of 74.0 beats per minute and a standard deviation of 12.5 beats per minute. And we first want to find the probability that one randomly selected woman has a pulse rate greater than 80 beats per minute. So we want probability that x here is greater than 80. Since we're only talking about one person, we are not using the sampling distribution of the sample mean. And as such, we could just use the regular normal distribution calculation. So for this, and I'll just quickly sketch it here to the right, we have a normal distribution with the mean here of 74 and 80 would be over here. And we're referring to the area above that. But of course, since SAS does not allow us to calculate the area to the right, we need to do the area to the left. So 1 minus the probability of x being less than 80. If we toss that into SAS, we would get ourselves a value of 1 minus 0.6844. And that rounds to about 0.3156. Now for B, we want to find the probability that a sample of 16 randomly selected women have a sample size rate greater than 80 beats per minute. Now we are told that we have a sample of size 16. And we're talking about the mean pulse rate. So because of that, the mean of the sampling distribution of x bar is simply 74 again. But now the standard deviation of the sampling distribution of x bar, and this is going to be 12.5 divided by the square root of 16. And if you do this out on a calculator, you get yourselves an answer of about 3.125. But 16, though, here is less than 30. But since we were told that it's normally distributed anyway, we could still do this. So we're fine. The picture for this is roughly the same thing as above. Only difference, though, being, and I did a bad job drawing that, but we have a mean of 74. 80 would be even further to the right. And we want the area above it. So probability that x bar is greater than 80. Same thing as 1 minus the probability that x bar is less than 80. This would be 1 minus 0.9726. And this gives us a probability of 0.0274. A very small probability indeed. Given that part B involves a sample size that is not larger than 30, why can the central limit theorem be used? That's because the population is approximately normal. Well, I should say, we were told it's normally distributed. But the population itself is the approximately normally distributed. And since the population is normally distributed, that's why we could use this central limit theorem. To identify significant results with probabilities, if under a given assumption the probability of a particularly observed event is very small, and the observed event occurs significantly less than, or significantly greater than, what we typically expect with that assumption, we conclude that the assumption is probably not correct. As another example, assume that the population of human body temperatures has a mean of 98.6 degrees Fahrenheit, and as is commonly believed, and the population standard deviation is 0.62 degrees Fahrenheit, based on data from the University of Maryland researchers. If a sample size of 106 is randomly selected, we will find the probability of getting a mean of 98.2 degrees Fahrenheit or fewer. The sample size is definitely greater than 30 here, right? 106 is definitely greater than 30. So the mean of our sampling distribution of x bar, as we were told, is 98.6 degrees Fahrenheit. And the standard deviation of the sampling distribution of x bar is 0.62 divided by the square root of 106. If we toss this into a calculator, we get an answer of about 0.06022197. So we need to find the probability that x bar is less than 98.2. So this distribution looks something like this. We have a mean here of 98.6. And we want to know, we're getting a mean of 98.2 degrees Fahrenheit or lower. So 98.2 would be over here-ish. And we want the area to the left, which is easy enough to do in SAS. For this, we get a very, very, very small probability. 0.000000000, that's 3, 0.00155. That's 10 zeros here. 0.000000000000155, which is basically very close to 0. But it's not entirely impossible, just very unlikely. The correction for a finite population, though, when we applied the central limit theorem, we assume that the population has infinitely many members. When we sample with replacement, the population is effectively infinite. When sampling without replacement from a finite population, we need to adjust the standard deviation of x bar. When sampling without replacement and the sample size n is greater than 5% of the finite population size n, we want to adjust the standard deviation of sample means. So the standard deviation of the sample means by multiplying it by the finite population correction factor of the square root of the population size minus the sample size divided by the population size minus 1. Thank you.